abstract nonsense. And if you read the abstract, you will have noticed it was a lot of nonsense. So that's a good starting point. I guess the goal of my talk today is to just give a gentle introduction to category theory to people that have not seen category theory before, and to see some ways that the concepts in category theory apply to other areas of mathematics. This, unfortunately, means I'm not going to get to prove very much. Most of this is going to be definitions and examples. But then, if you want to go and read any number of books about category theory, you can come and look at some of these if you want to. There's a book called Category Theory by Steve Audi. This is the book that I learned category theory from the first time. Steve Audi is now my PhD advisor. That's a pretty good book. Categories for the Working Mathematician by Saunders MacLean. He was Steve Audi's PhD advisor. This is like the canonical textbook in category theory. A bit old though, it was written in the 70s. And another one, Elementary Categories, Elementary Toposes, written by Colin McClarty back in the 90s, I think. This is like pretty good. So if you're interested in learning more category theory, you can read those books. This is really just meant to be a kind of smattering of categorical concepts in various areas of mathematics. Now, I decided on the title of my talk before I started writing my talk, and then I had a bunch of unexpected teaching duties to do today. So unfortunately, my talk is not as well prepared as I would like. So you're going to have to bear with me if I'm umming and ahhing a little bit, but I think I should be okay. So the outline for what I want to do. First of all, I want to give some motivation. Why do we even care about category theory? Why do people like me spend our lives studying this subject? I'm then going to define what a category is. So I'm going to define categories. After this point it becomes a bit more dubious. So I'm probably going to define what a functor is. This tells you ways that you can translate between categories. This is a natural notion of a morphism between categories. Then I'm probably going to talk about some limits and colimits. I'm probably not going to tell you what a limit or a colimit is, but I will give you some examples of limits and colimits and instances of when they appear in life. Yes, the sky is indeed the colimit, Michael, very good. You've been learning. And if I have time, I don't want to speak for too long today, but if I have time, I'm going to tell you all about adjunctions, because I think in all of elementary, first glance at category theory, adjunctions are my favorite thing, because they're incredibly powerful. You can do a lot with them. They give rise to nice objects called monads. Monads are incredibly useful in computer science and also in elementary, in like algebra. If you're doing algebraic theories, monads come up in that. It's just very useful. So, okay, I was going to do some motivation. I'm going to motivate a lot of what I'm going to talk about just by giving a bunch of examples. So, the first observation that I should say, this is not a historical account of why category theory came about. Category theory was devised in the paper by Saunders MacLean and Samuel Eilenberg in 1945 when they were doing homotopical algebra. They defined the notion of a natural transformation and worked backwards through functors and categories to get to what they wanted to do. We're not doing that. But a way it could theoretically have come up in history is based on the observation that all over mathematics you have sets with some kind of structure on them. So, all over the place, you encounter things that form sets with structure. And usually, you don't just study these sets with structure in isolation. So things like sets, groups, rings, modules, vector spaces, topological spaces, compact Hausdorff spaces, norm spaces, Banach spaces, metric spaces, all your favorite spaces, all your favorite algebraic gadgets. If you studied them in isolation, you wouldn't be able to say very much. Even graphs. Graphs are another example of a set with a kind of structure. They're equipped with some kind of function. They're equipped with a notion of a function between the sets that interacts with the structure in a certain way. So a function which interacts with the structure. Nice one, structure. And just noticing this helps you find out what the category should be. So just to see some examples here, the basic one are sets with no structure, and functions between sets, they don't have any structure to do anything with. So sets and functions are an example of this. You've probably all done abstract algebra, so you've seen groups and homomorphisms. Everyone in their first course in abstract algebra sees a group, and then shortly after a group has been defined, you define homomorphisms of groups, because groups in isolation are fairly boring. You can look at their subgroups, you can look at their normal subgroups, and you can decide if they're simple and all that kind of stuff, but it's the interactions between groups that make things really useful. You could look at rings and ring homomorphisms, you could look at modules, module homomorphisms, etc. There's various notions of space and continuous maps. Between spaces, continuous maps interact with the openness, right? So if you define a topological space, that's a set equipped with the notion of an open set. The continuous maps interact with the open sets by saying that three images of open sets are open. Metric spaces, you can define continuity in another way in terms of the distance. You could have, say, metric spaces and isometries. That's another example. I mean, I'm not going to keep going on this list forever, but you get the point, right? There are loads all over the place. There's sets with structure, and then there are functions preserving that structure. If you looked at norm spaces, you could have a norm space together with a map that interacts nicely with the norm in some way, isometry, or a Lipschitz. Is it Lipschitz? That's an example of a map of norm spaces. So there's all sorts of sets with structure and functions all over the place. So this is like part one of this is like the first observation. This observation in itself is not really enough to make categories interesting. And so I'm going to make another observation. Another observation is that all over mathematics you see things that look eerily similar. And you might wonder what the reason is behind that. So, different areas of math. They often contain similar looking things. And this is something that you've probably encountered for yourself from an early age. You become tempted when you're first learning, you take your first course in proofs and you see set operations defined, and you want to think about intersection, and you define intersection in terms of conjunction. You've got and then you've got intersection of sets, and they behave in similar ways. So just to see, I'm going to look at a couple of these things. One of them is products of sets. So what is a product of sets? So if you take two sets A, B, well, their product is the set A cross B, right? It's the set of ordered pairs of elements of A in the first component, elements of B in the second component. This is equipped with two natural projections down to A and B. This here is a projection down to A, projection down to B. This just returns the first coordinate, the other one just returns the second coordinate. This has a cool property. And the cool property is this. If you give me a set X and two functions, f and g, f is a function from X to A and G is a function from X to B, then there is a unique function, say H, going from X to the product, such that these triangles commute in the sense that H of, well, I guess the first projection of H of AB is equal to F. Sorry, that should just be A, what I'm doing here. Sorry, F of X. There we go. Is equal to F of X. That's the projection onto A. And the projection onto B of H of X is G of X. So this is half of the observation I'm about to make. In other words, there is a set, it's equipped with projections to A and B, and it has this nice property that if you map into A, map into B, then there's a unique function into A cross B. Namely, H of X is equal to the pair F of X, G of X. And this completely characterizes the product. But the fact that this characterizes the product is not going to be too relevant for what I'm about to say. I'm going to compare this with what happens in logic. And in logic, when you have the conjunction of two formulae, phi and psi. So if you take two formulae phi and psi, well, phi and psi implies phi. Right? Now when I draw an arrow, I mean implication. I don't mean like a function. Phi and psi implies psi. Okay. So, oh, I've drawn this too high. I'm going to draw it a bit lower. So, but here's a cool fact. If you give me some other formula that implies both phi and psi, then it implies phi and psi, right? This is obvious. This is stuff that you just do in your head. You don't even, you know, if you're studying formal logic, maybe you care about this stuff. But if you, like most of you, are in analysis or combinatorics or whatever, like, you use this kind of reasoning. If you're trying to prove that two things are true, you prove that one of them is true and you prove that the other one is true, right? Duh. So I'm not telling you stuff you don't know here. But the categorically minded would look at this and think, this is the same thing. And so that's, I guess, the second third of the motivation that I was going to give. So the first one is, you've got these notions of sets with structure and functions that preserve the structure appear in a local place. Another observation is that different areas of math have very similar looking things in them, even though they say very different things overall. And another observation, I'm going to erase this for now. Another observation that you can make is also, I'm also going to compare sets with logic again. Computer scientists are very familiar with currying. And since most of you are eating curry, this seems like a perfect opportunity to talk about it. So currying and uncurrying is the observation that a function from a product correspond with functions that take in elements of A and spit out functions from C to B. So this is the set of functions from B to C, not C to B, sorry. So the idea here is that if you give me a function f, then this corresponds with a function f bar. So f bar of A, it takes in elements of A and it spits out functions from B to C. Apply that to an element B, and what you get out is just f of AB. Right, so elements here are pairs, f of AB is an element of C, and so on. Right? This is called currying in one direction, uncurrying in the other direction. This comes up all over the place in computer science, where you don't want to necessarily talk about products all the time, you just want to express everything in terms of functions. So this is something that comes up in set theory, and then there is an analogous thing that comes up in logic, which is that if you know that phi and psi together imply chi, then this is equivalent to knowing that if you know phi, then psi implies chi, right? If this is true, then if this is true, then they're both true, so this is true, and vice versa. So here are two different things. This here is a statement about logical formulae. Here is a statement about sets. Likewise over here, here's a statement about sets, here's a statement about logical formulae. Something similar is going on. And so the real question is, how can we make sense of all of this? And my answer, which is not everyone's answer, but my answer is with category theory. Or categories. And so that's kind of, this is the motivation. This is what I'm trying to tell you about in this talk. So before I get started, do people have any questions about the joys that are to come? So I want to convince you before I get started, category theory has a certain reputation. I said in the abstract for the talk, which you may or may not have read, there is a mathematician, in fact a category theorist called Peter Freyd, who once said, category theory, or rather the purpose of categorical algebra, is to prove that which is trivial is trivially trivial. So this comes from a common idea in math that category theory doesn't prove anything. and that all category theory does is reword things in mathematics. Unfortunately, what I'm going to do today is not going to disprove that claim at all. So really you should think about category theory as being more of a tool than a theory. There are not that many theorems of pure category theory, or I mean, there are, but pure category theory kind of took off in its own direction, but as far as the rest of mathematics goes with its interaction in category theory, there aren't that many theorems that are useful. One of the biggest theorems in category theory is called the Oneida lemma, right? One of the biggest theorems in category theory is called a lemma. So that should give you an idea about why I'm not trying to claim that category theory is going to change the world, but it will help you understand questions like, what is going on here, right? And this appeals to me because I really want to find the truth, right? And if I can find why these two things are the same, then maybe I'm partway there. But maybe I'm not. I also want to say, when I was doing my undergrad in my category theory course that I took, the professor would regularly set exams that had an essay question. And in the year that I took it, the essay question was, category theory is a tool for proving that which is trivially trivial. Discuss. And you had to give a mathematical answer to that question. And fortunately, there was another option, which was to prove the special adjoint functor theorem, so I did that. Anyway, I should tell you, so let's move on to actually telling you what categories are. So, there are two ways that I can put this. And the simplest way is that you shouldn't fear categories because all they are is a special kind of algebraic object. So you define groups by specifying a set, a unit element, inverse, group operation, and then specifying a bunch of axioms. The same thing is true of category theory, of categories. So the intuition about why categories are defined like this comes from the stuff that I raised over here about sets with structure and functions that somehow interact with that structure. So what is a category? So a category, which I'm going to write with a curly C, consists of the following data. So this is, classical algebraic presentation. You present the data and then you present the axioms. So the data is a set of C of objects. So you think about the objects of a category as being the sets, being the groups, being the rings, the topological spaces, the modules, the metric spaces. The objects of the category are the sets with the structure. But they don't have to be. And we'll see some examples of categories that don't have that kind of behavior soon. So if you give me any two objects, then there's going to be a set of morphisms with domain A and codomain B. So for all A and B, there is a set or a class. I mean, I'm calling these things sets. There is a foundational question to be answered, which I'm going to completely brush under the rug. So there is a set CAB of morphisms, also known as arrows, from A to B. So you write elements of this thing in the form, so if you write an element of this thing, you just write F colon A arrow B. So this looks like a function, but really I'm just specifying an element of a set, the set corresponding to, this is called the Hom set, if you like. So if C were the category of groups, then the objects of C are the groups, and the elements of this set are group homomorphisms from the group A to the group B. If this were the category of topological spaces and continuous maps, then the objects would be topological spaces. The elements of this set are continuous maps from A to B. That's another example. In addition, so if you give me any object of C, then there is something called the identity morphism from A to A. And this arises because whenever you have a bunch of sets and a bunch of functions that interact with the structure, usually the identity function is one of those functions. So the identity function on a space is continuous. The identity function on a group is a homomorphism. The identity function on a module is a linear map of modules, whatever you want to call it. the identity map on the metric space is an isometry, right? So another observation is that these things are usually close in decomposition. So if you give me a morphism from A to B, and you give me another morphism from B to C, then I'm going to give you a new morphism G composed with F from A to C. This just says things like the composite of two continuous maps is continuous, the composite of two homomorphisms is homomorphism, and so on. Then there's a bunch of axioms, and the axioms I'm going to skim through. The axioms say that identities act trivially with respect to composition. So if you compose with the identity, you get your function back. So this says that f composed with the identity on its domain is equal to f, which is equal to the identity on its codomain composed with f. That's pretty simple. That's the identity axiom. There's one more axiom, which is associativity of composition, which says it doesn't matter if you compose G with f first, or if you compose H with G first, because you get the same thing out. And that's it. That's a category. So that's all it is, right? It's a set, a family of sets indexed by that set, together with identity, morphisms, a composition operation that satisfies these two axioms. And so let's just look at some examples very quickly. So there's set. This is the category of sets and functions. So the objects are sets, the morphisms are functions. I'm not going to keep writing out what the objects and morphisms are, but group. It's the category of groups. No, it's the category of groups. The objects are groups. The morphisms are homomorphisms of groups. The identity morphism on a group is just the identity function, which is a homomorphism. Composition is defined usually. There's a category of commutative rings, modules over a ring. That's another example. Category of topological spaces and continuous maps. Category of metric spaces, and they have suggestive names. So these are the examples we've already looked at. There are a bunch of categories that don't look like sets with structure and functions preserving that structure. So I'm going to tell you a couple of examples of those. Exactly 2 examples of those, in fact. These axioms up here look suspiciously similar to axioms for another object you know and love from mathematics, namely a monoid or even a group. If you think about the identity as being like the unit element of a group, then multiplying something by the unit is the same as multiplying by the unit on the left, which is the same as getting your thing back. And if you think about the group operation as being composition, this looks a lot like a group or a monoid, right? And in fact, you can, from any monoid or any group, you get a category. So I'm going to say group just because groups are more familiar to people. Monoids are just groups that don't require inverses to exist. Then this is going to give me a category G, which I'm going to write G with a little blackboard boldface. The objects of G, there's only one of them, blob. So I'm going to think about this blob as representing something that the group could act on, and I'm going to make this precise at some point in time. So, okay, for every object of G, I need to specify what the morphisms are from blob to blob. Right, there's only one object of G. So I'm going to think about the elements of G as being morphisms from blob to blob. So the identity morphism on blob is just the unit element of the group, the identity element. And the composition operation, I'll call it H and G, is just the group operation. And okay, well, what do you have to check? Well, I've just specified all the data, and this is true because when you multiply by the identity element, you get your thing back. And this is true because the group operation is associative. So this works for monoids and it works for groups. So it's kind of weird, right? You don't think about this blob as necessarily being anything, it's just a blob. But the elements of the groups form a morphism, the morphisms of a category, which is pretty cool. So what's another example? I was going to tell you about posets. So if P is a pre-order or poset, That is, it's a set equipped with some notion of ordering. Preorder means reflexive transitive relation. Poset means it's also antisymmetric. So if P is a p-order, then this is going to give me a category P. And the category P, well, the objects of P are just the elements of the poset. And I'm going to say that a morphism from one element of P to another exists if and only if the domain is less than or equal to the codomain with respect to the relation on P. So I say, so the morphisms from P to Q, there's either one of them, call it whatever you want, if P is less than or equal to Q, and not otherwise. So nothing otherwise. So, what do we have to check here? Well, the identity morphism is going to just be the assertion that A is less than or equal to A, right? And composition corresponds with transitivity. If A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. The axioms hold, well, these are just trivial, essentially. This one tells you that if you know that A is less than or equal to B, which is less than or equal to C, and you deduce that A is less than or equal to C before you deduce that A is less than or equal to D, then, you know, so the axioms hold very trivially in this category. I'm going to do one more. I'm going to do one more because this is the graduate student seminar. And in the graduate student seminar, there is a tradition that seems to have been lost on the last few speakers. A graph is a pair VE, where V is a set and E is a subset of the pairs of elements of V. Now, I'm going to okay, I've defined the graph. This tradition is now complete. So I'm now going to modify it. A directed graph is a pair VE, where I guess you remove the pairs VV. Every graph induces a category, right? So if you just draw a directed graph has edges that look a bit like this, maybe there's one going back as well. Right, this is a graph. If you think about the vertices as being the objects of the category and formal composites of the edges as being the morphisms, then this gives rise to a category. So this gives rise to the category generated by the graph, the directed graph. So, you know, the morphisms, there's the identity in all of these blobs, which isn't represented in the directed graph, but they exist because they have to, because it's a category. And then this thing is a morphism. Each of the individual edges is morphisms, but then also this composed with this is a morphism. And this composed with this, composed with this, composed with this, composed with this is a morphism, and so on. So you freely generate the category from the graph. And in fact, that free generation comes from an adjunction, which at this rate I'm not going to get to talk about. But I thought I'd mention it anyway. So are there any questions before I keep talking? Well then, let me keep talking. So, what did I say I was going to do next? I told you I was going to tell you about functors. Functors are cool. Functors translate from one category to another. Functors are the obvious notion of homomorphism of categories. So, this is number 3. And you can't say functor without fun. So if you take two categories C and D, I should say, one of the perks of being a category theorist is you get really good at writing your curly letters. You just have to. So a functor F from C to D. So what this does is it's a way of sending objects of C to objects of D, morphisms of C to morphisms of D, in such a way that domain, codomain, composite, and identity are all respected. So this is just the natural idea of a morphism of these algebraic gathers. So you've got the objects of A, then you go to objects of D. If you give me a morphism F from A to B, then this induces a morphism FF from FA to FB in D, and these have to respect identity. So F of the identity is just the identity on what happens to that object, and likewise composition, F of G composed with F is FG composed with FF. So that's it. It helps to see examples. I'm not going to spell out the definition for too much longer. I'm going to leave that on the board because it's interesting. I want to leave that on the board because it's interesting. I'm going to erase this. So let's look at some examples of functors. There are some really stupid ones. I mean, there's identity functors on a category. They're really dumb. There's a choo-choo train outside, which has stopped honking temporarily. So there are a bunch of things which we call forgetful functors. So for example, they're usually denoted by U. I don't know why U is the letter used.
Is it like some other language, or?
Maybe. I don't know. Well, so you might think that you want to call them F. And I'm actually, we will soon be seeing why you don't want to call them F. So I can agree that they shouldn't be F. But the next letter is O. I don't know, anyway. So, for example, if you take any set equipped with extra structure, any set whatsoever, equipped with extra structure, then you can just forget that it ever had that structure. So the forgetful functor from groups to sets sends a group to the underlying set and a homomorphism to the underlying function. It just forgets that the thing was a group ever, right? So this just forgets the group structure. It sends a G to the underlying set and it sends a homomorphism to the underlying function of groups. There's nothing more to it. It sends a ring to the underlying set, ring homomorphism to the underlying function. It sends a topological space to the underlying set. It sends a, these are all boring, right? I mean, they're not boring to me, but they're boring to some people. There are also free functors, and this is why I don't want to call forgetful functors F, because I'm going to be calling the free ones F. If you give me a set, I can freely turn that set into a group, right? The free group. So F goes from set to group. It sends a set to the free group on X. The free group on X, well, what do? You take formal inverses of, well, yeah, you take strings and formal inverses of the elements of X. What's a simple example? The free group on one generator is the integers, because you can, if you have a set that only contains the letter X, then the free group on X has like the empty string, that's the identity, has X, X squared, X cubed, X to the fourth, all the way up. And it has all the negatives, because the inverses have to exist, and that's isomorphic to the integers. There's another bunch. So, for example, if you want to turn a set into a topological space, there are two natural ways of doing this. You can put the discrete topology on the set, or you can put the indiscrete topology on the set. That's another example. So discrete topology, every set is open, every subset is open. Indiscrete topology, only the empty set and the full set are open. So there are a couple of examples of free functors. How much more do I want to do? Oh yes, okay. Right, I was keeping this on the board because I want to show you some cool examples of it. Can anyone see what a functor from a group considered as a category to the category of sets must be? So just think about this for a second. It must send an object of G, that is blob, to a set. It must send a morphism of G, that is an element of G, to some kind of function on the set to itself. Functors from the group considered as a category to the category of sets are precisely group actions. So a functor is just, if I call this thing alpha, this is precisely a group action on a set. There's nothing more to it. A functor between two coset categories is one that sends objects of P to objects of Q, so elements of P to elements of Q, and it sends elements of this thing to elements of the other thing. Well, an element here exists if and only if P is less than or equal to Q, which means that it tells me that P less than or equal to Q must imply that FP is less than or equal to FQ. So functors from P to Q are just order preserving maps, which is kind of funny. Anyway, those are functors. They just send objects to objects, morphisms to morphisms, they respect identity, they respect composition, but there's a bunch of examples. And now I'm deciding whether I want to tell you about adjoints or if I want to tell you about limits and colimits. Ooh, I'm going to do both. I am an ambitious man. I also want to tell you about duality. I want to tell you about tree sheaves. I want to tell you about everything. Unfortunately, I can't because we are much time. Okay, so I can't count. What did we get to? 3? So I guess we're on to 4. Limits and colimits. So I want to say the first observation that we made at the beginning, that sets with structure and functions that interact with that structure, that compose nicely, that behave well with identity, they appear all over mathematics. We have just abstracted that idea into this notion of a category. That's the first thing that we did. Here's a bunch of examples, we've seen them now. So the first of the 3 observations is now done, right? We've done it. And we've even done some more. We've defined functors, which I'm going to get back to momentarily. Limits and colimits are the thing that are going to tell us why the 2 things that we saw, remember the product of sets and the conjunction of propositions, why those 2 things were essentially the same. We're going to come up with the notion of a product in a category which instantiates to the product of sets in the category of sets, and it instantiates to the conjunction in the category of logical formula. Logical formula is a coset category of logical formulae ordered by provability. So what am I going to do with this? I'm going to give you the idea. I'm not going to give you the definition, because the definition, as I'm sure anyone that is currently taking category theory knows, is somewhat ugly. But the idea of a limit of a diagram, I haven't told you what a diagram is. A diagram is just a bunch of objects and morphisms in a category, right? That's all it is. So this is just a bunch of objects and morphisms in a category, which themselves form a subcategory and a bunch of other stuff, but you'll get the idea in a moment. What is this? Well, you can think of a limit as being a bit like an infimum. It points to, in the sense that it's less than or equal to, it points to all of the objects and the morphisms of this diagram somehow, and it does so in a maximal way. So it's a way of, in some sense, mapping into the diagram in the largest possible way. And what the hell do I mean by this? Well, let's have a look. So for example, if my diagram shape is just blob, blob, what this means for the diagram in my category is that I just have a pair of objects, right? If the diagram shape is just blob, blob, I'm going to draw a bunch of blobs and arrows, that's going to be my diagram shape, map it into the category. So here I just have blob, blob. Then what is this? Well, the limit of this is going to be some way of mapping into the diagram, which is the largest possible way of doing that. Which is to say that if I map into the diagram again, then there's going to be some kind of factorization through here. What does this look like? This looks like the product of sets. This looks like the conjunction of 2 propositions. So if you take C to be the category of sets, or the category of groups, or the category of topological spaces, this just gives you the product. If you take C to be the coset or it's a pre-order, but I'm going to call it a poset, of logical formulae ordered by provability, then this gives me the conjunction. If this is an arbitrary poset, this gives me the infimum of two things. Products generalize even further. You can have products of arbitrarily many things. That's pretty funky. What are some other examples? So suppose my diagram shape was this. Do any category theorists want to tell me what the limit of a diagram of this form is? Okay. Pullback! Right, so this is going to give me something called a pullback. So what does this mean? So this means that inside my category I have something that looks like this. So what's a universal way of mapping into this? Well, it's going to be some object equipped with morphisms to each of these things. It's all going to have a morphism to C, but because all the composites are going to work out, this morphism is going to be equal to those two composites, and so I don't need to write it. And if I map into this diagram in another way, then there is going to be a unique factorization here. And I'm going to tell you what this does in the category of sets and do a quick example. So in the category of sets, what this looks like is, so if I call this function f, if I call this function g, these really are functions now because the morphisms in the category of sets are functions between sets. This thing, this p called a pullback, is the set of pairs in the product a cross b, such that f of a is g of b. And this is often denoted by a cross b with a little subscript c. If you've ever done any abstract algebra, you might have seen this kind of thing before. There are a bunch of cool examples of pullbacks. For example, if you take a function from a to b, and then you look at the identity on b, and you take this pullback, then what you get is the graph of f. It's the set of pairs a, b, where f of little a equals b. So it's the set of pairs a, f of a, where a is an element of a. It's the graph of the function. Why am I doing this? I'm doing this because I want to dualize everything. And I've not told you what duality is, but duality is like so cool. The dual notion is that of a colimit. An infimum is to a supremum as a limit is to a colimit, as a product is to a coproduct, as a pullback is to a putout. So what a colimit means, well now, instead of being the largest way I can map into my diagram, it is going to be the smallest way I can map out of my diagram. Which is to say, it's going to be something equipped with functions from a to c, functions from b to c, such that if I map out again, then there's going to be a unique factorization like this. When you take the category of sets, well, okay, let's have a look at this. I can include a and b into the disjoint union. A function from the disjoint union is specified precisely by specifying the function on the a part of the disjoint union and on the b part of the disjoint union. So that's where this unique factorization comes from, is to specify a function from the disjoint union of a with b is precisely to specify a function on a and to specify a function on b. What does this mean in the logic? If I know that phi implies chi, and I know that psi implies chi, then I know that their disjunction implies chi. Moreover, phi implies the disjunction and psi implies the disjunction. Disjunction means or, right? So, and is dual to or. Coproduct, disjoint union is dual to product. And category theory is what allows me to say all of this stuff. Now, if there appears to be no structure in what I'm saying, by the way, that's because there is no structure in what I'm saying. But I just want to show you a smattering of these things. There is also a dual notion of this called a push-out. You can describe a dual notion called a cograph of a function, a notion which is heavily overlooked. Have you ever done functions with you ever taught concepts and you tell people that functions can be drawn like this? This is a cograph. This is dual in a categorical sense to that of a graph. Now, if you're interested in the details, you can speak to me afterwards, because it's cool. Anyway, I'm now going to tell you about adjunctions. So, if you didn't understand this business about limits and colimits, don't worry. I won't mention any of it until the very end of my section on adjunctions. And since we're doing so well on time, I'm very quickly just going to give you a very quick recap of the most important things that you need to know so far, which is that a category just has objects and morphisms. You think about the objects as being things like groups. You think about the morphisms as being things like homomorphisms. And the functor is just a way of translating these notions from one to another. So a functor from a category C to a category D sends objects to objects. And it sends morphisms to morphisms. And it does it in such a way that identity and composition are respected. So I'm not going to tell you what an adjunction is just yet. Instead, I'm going to show you some curiosities. So I guess I'm on adjunctions. Anyone that's ever done any functional analysis will be aware of the word adjoint at some point, right? Or if you've ever done linear algebra, you'll know that if you have a linear operator on a space, then its adjoint is something that behaves in a certain way with respect to an inner product. This is where the name adjunction comes from. It's just cosmetic. It's just because they look similar. There is there's no like deep connection between the two things beyond the fact that they look very, very similar. So I told you before about currying functions, and I told you about this whole, if the conjunction of two propositions implies something else, then you get this like, one implies the other kind of thing going on. Let's look at some other things along those lines. So we saw that functions from a product to another set correspond, that's what this double line is going to mean, they correspond with functions from A to the function set, right? So there's one example. We saw that essentially proofs that phi amp psi imply chi correspond with proofs that phi implies that psi implies chi. It's also fairly obvious. I'm going to keep drawing things like this until things become more clear. So, what's another correspondence? Well, if you've ever seen a free group in abstract algebra, it's usually defined to you in two ways, or it's defined in one way and characterized in terms of another, or you prove something. The free group is characterized by the following property. So if X is a set, then the free group is characterized by this. There is an insertion of generators. So this sends every element of X to just itself in the free group. And this has the property that any function from X into a group extends uniquely to the free group as a group homomorphism. So this tells you that functions from a set to a group, these are just functions, they don't have to be homomorphisms, just functions from a set to a group correspond with group homomorphisms from the free group on that set to the group, now as group homomorphisms. What's another example? I'm going to cook up some more of these. Aha, right, so here's another example.
So just to be pedantic on the top, would we write maybe like UG?
Yeah, so this is the underlying set of the group. Yeah, you can think about it however you like. But I'm just going to write it as G for the purposes of doing the intro, but yes, like UG, like the forgetful functor applied to G is really what's happening. In fact, you know what, I will do that. This here is the underlying set. Okay, so what else? Well, I'm going to screw this up. No, I'm not? Okay. So if you give me a function from a set to an arbitrary topological space, so this here is a topological space. Again, okay, I'm going to call it UA. So A is a space. UA is the underlying set. Every function with discrete domain is continuous. Because the preimage of an open set is a subset of the domain, and if all subsets are open, then ta-da, right, you've got your thing. So this corresponds to continuous maps from what you get. Actually, tell you what, right, I'll call this A tau, and then I'll just call this A. So a function from x to the underlying set of the space corresponds with a continuous function from x with the discrete topology to A with whatever its topology was. There's another example. What about the indiscrete topology? Well, the indiscrete topology, if the codomain of your function has the discrete topology on it, the only open sets are the empty set and the full set. The preimage of the empty set is empty. The preimage of the full set is the full set. They're always open. So what this tells you is that if you give me a continuous map from any topological space to a set with the indiscrete topology, then that corresponds precisely with functions from A to X. So any function with indiscrete codomain is continuous. This says that any function with discrete domain is continuous. There is a reason why I'm doing all of this. And the reason is this. These all exhibit very similar categorical behavior. I'm going to do one more, and this is another example from topology, and I'm doing it because Andy is in the room, and it was his birthday yesterday, so it's a birthday present for Andy. So, if you give me a topological space, then the stone check compactification is a space denoted beta x, right? You may have seen it called the beta compactification before. This has the following property. There is a map from every space into its beta compactification. This has the property that if you give me a continuous map from X to any compact space, then that extends uniquely to a function from the beta compactification of your space. So this says that continuous maps into compact spaces extend uniquely to the beta compactification.
Wait, can you do this without Hausdorff?
Hausdorff is required for this to be, maybe you need a locally compact Hausdorff for this to be, sorry, no, yeah, this is compact Hausdorff.
Oh.
Yeah, that's right. So yeah, so it's like so what does this mean in terms of these little blobs that I've been drawing? Well, it means that continuous maps from X to compact Hausdorff spaces just thought of as spaces correspond with continuous maps from the compact Hausdorff space beta x to the compact Hausdorff space k. And what I'm going to do now is tell you what the hell is going on in all of these cases. Okay? And this is an adjunction. What's happening in all of these cases is there is a left adjoint and a right adjoint. The left adjoint is the thing that happens on the left. In this case, the left adjoint is product with B, conjunction with psi, the free functor, the discrete topology, the forgetful functor, and the beta compactification. These are all the left adjoints. So what does this mean? So if you give me a category, and the category, and the functor in the other direction, then I'm going to define what it means for there to be an adjunction between these two things. So we say F is left adjoint to G, or equivalently G is right adjoint to F, and we write F backwards turnstile G to denote this. What this means that C morphisms from, say, where are we going? Other way, from X, how about this? From C to G of D correspond naturally with D morphisms from FC to D. So these look like Galois connections. Galois connections are precisely adjunctions between posets, which is kind of cool. So let's have a look at what the categories are in all of these cases. This says that the product with B is left adjoint to exponentiation IB in terms of taking function sets. This says that if you apply this to, and there's a naturality condition here, which I'm not going to spell out. So these correspondences have to behave well with respect to the morphisms in the domain and codomain categories. This one here says that conjunction with psi is left adjoint to psi proving stuff. This one tells me that this is called the free forgetful adjunction. So maps of sets, maps of underlying sets correspond with homomorphisms with the free domain. This extends not just to groups, but also to rings, any other algebraic category. This will work. This tells me, so okay, what have we got? Well, these two together actually give me, so I've got the category of topological spaces and the category of sets. What this tells me is that the discrete functor is left adjoint to the forgetful functor, and it tells me that the indiscrete is right adjoint to the forgetful functor.
Wait, so just so I remember this, so the right refers to right side of the arrow.
It refers to the right side of the arrow.
Okay.
Yeah, so I mean, these could be written either way around, but it's the right-hand side of the arrow. So this means that if you forget the topology and map into any set, then this extends uniquely to a continuous map. And likewise, if you map from any set, then this extends uniquely to a map from the discrete space.
So it's saying like the indiscrete functor is right adjoint.
The indiscrete functor is right adjoint,
Yeah.
because
It's on the right.
it's on the right.
Yeah.
Okay. So what does this say? Well, this is really talking about the inclusion from topological spaces. Sorry, it's talking about the inclusion. K-house is the category of compact Hausdorff spaces. Compact is spelled with a K because Hausdorff is German. So this tells me that the inclusion is left adjoint to the stone check compactification.
Wait.
Other way around.
Right, yeah.
So this tells me that stone check compactification is left adjoint to inclusion, because if you just treat your compact Hausdorff space as a space, then continuous maps correspond with these things. Yeah, so all these things are adjunctions. And so now I'm going to sum up the talk. And why am I erasing the definition I just gave? I'm going to sum up the talk by stating a theorem. And the theorem is left adjoints preserve colimits, and right adjoints preserve limits. What does this mean? Stone check compactification is left adjoint to another functor. This means if I take the colimit of any two spaces, then I can either apply the stone check compactification before, or I can apply it after. It so happens that the coproduct of two spaces in the category of compact Hausdorff spaces is their disjoint union, and the same is true in topological spaces. So this tells me, for example, the stone check compactification of a disjoint union is isomorphic to the Stone-Chekhov activation of X disjoint union Stone-Chekhov activation of Y. Because we saw that disjoint union is a coproduct. Another example, the forgetful functor from topological spaces to sets has both adjoints. This means the product of spaces, if you take their underlying set, is the same as the set of the underlying, the underlying set of a product or a coproduct is the same as the product or coproduct of the underlying sets, which is to say that if you do any kind of Cartesian product or pullback or equalizer, any kind of product, then the underlying set is just going to be what you get when you compute this thing in the category of sets, which is kind of cool. Blah, blah, blah. This is an extremely powerful theorem, which if I had more than 10 minutes to talk about, I would. But instead of talking about it for 10 minutes, I'm just going to stop. So thank you all for listening. I hope you have enjoyed this little tutorial on category theory. Are there any questions? Yes?
Wait, so I'm a little bit worried about what you wrote regarding colimits and beta compactifications. What if I try to take the colimit of a much larger diagram?
Such as?
Countably many spaces.
Well, so...
Or does that not exist in the category?
No, it exists.
Is it?
But here's the catch.
It's not the, yeah, okay.
For example, the coproduct of countably many singletons in top is the discrete space with the natural numbers
And
as its point.
Oh, and then in K-house, it's going to be the...
If you compute the coproduct in K-house, you're going to get something else, and that just happens to be the Stone-Chekhov activation of the natural numbers. Yeah.
So it's how you interpret colimit.
Okay. It's colimit in the category. Yeah.
Any other questions?
Well, if I have whet your appetite, this is the moment to start with. Category Theory by Steve Howard. Okay, thanks.